Hello everyone. We have been discussing the volume change behavior of soils, especially the clays. Today let us understand with simple experiments how the volume change of different clays can be understood. Let me demonstrate the variation in volume of the soil in water and kerosene, which is non-polar. Here we have three different soils. One is sand, which is inert, which does not react to water or kerosene, and we have bentonite, which is rich in montmorillonite, which reacts with water, and creosote again, because it's non-polar, it does not react. So the clay water interaction, because of the mechanisms involved in clay water interaction, the change in the volume of these soils can be understood with simple experiments, which is called freeze swell index or equilibrium sediment volume. And we have kaolin, which is rich in kaolinite mineral. The volume of this kaolinite mineral in water is smaller than in the presence of kerosene. So let us understand why the volume of these soils or clays change with different interactions with water and kerosene. I have my research team here. They would help me in doing these tests. Let us understand now. We have two cylinders. In one cylinder we have sand, dry sand we have put, and in another cylinder we have sand kept in water. Here you can see the volume of the sand in both the cylinders is nearly same. So that is because the sand does not react with water. So because of that, the volume is nearly same. On the other hand, if we have bentonite, let us see what happens. Here we have taken 2 gram of bentonite clay. We have a glass jar, glass beaker. Soil will be mixed now with water, but however for mixing we require Leb shaker so that thorough mixing is possible. The dry sample is added to a glass beaker and water is added. So now this is normal mixing is not possible, so therefore this will be placed in a shaker and will be continuously stirred or mixed in the orbital shaker. Here we can specify the speed and we can set the time. So normally this is how the sample is placed, and we can set the speed, and as slowly speed is increased it will start shaking. And considerable time is required for bentonites for mixing, and once the sample is thoroughly mixed, this will be transferred into glass jar to make 100 ml solution, and sedimentation will be allowed. Now you have 2 gram of clay, dry bentonite powder, which is available in 100 ml glass cylinder. Finally we thoroughly mix it again, and then we let it settle for equilibrium. Now particles slowly settle under gravity. This takes enormous time in case of bentonites. We have a clay water cylinder which is prepared earlier, much earlier, which is shown now here. So here you can see that there is a clear water that is formed, and you can see the interface between clay and then water. If you look at the volume of the clay now, this is significantly high. This is because the formation of diffused layers. Let me explain on the board now. When we have a cylinder, where we placed clay in it, when it is mixed, with 100 ml of water, which forms a clear clay water solution at equilibrium. This is the equilibrium volume. If sand of that amount is taken and then put it in water, it does not exhibit that much of volume expansion or volume change. Volume essentially remains same as we have just seen. In case of clay, volume expands and the equilibrium volume is significantly higher. This is because when you consider individual particle or clay platelet, which is a thin, slender particle or platelet, the thickness is around 10 angstrom units, nearly 1 nanometer for smectite particles, that is bentonite, and this is a slender particle, platelet. Because of the negative charge on the surface, it has a formation of diffuse double layers around individual platelet. So the diffuse double layer around individual particle or platelet is significantly high. The thickness could extend perhaps 50 to 100 orders of magnitude higher than the thickness of the platelet. It can even extend to higher value depending on the surface properties of individual clay platelet or individual clay or a given clay, which defines the plasticity of the clay. So now the electrostatic potential around individual platelet varies in this manner, and this is the thickness of diffuse double layer, which is represented with small d around individual clay platelet. If I have two clay platelets, which has just started interacting each other and they have diffuse double layers formed, now if this is the particle thickness or platelet thickness and this is the thickness of diffuse double layer from two different particles, if one particle diffuse double layer thickness is called d, then it is total value is 2d. So we can relate this thickness of diffuse double layer with void ratio, and from void ratio the equilibrium volume can be related. So it is very clear to understand how the equilibrium volume is such a significantly high value. So here the void ratio, we define void ratio as volume of voids by volume of solids. In this case, if you consider the volume of voids as, this is the volume of void space, this is particle, this is another particle. So the volume of voids can be obtained because this is the space which represents the volume of voids. So the volume of voids can be obtained as 2d times the surface area, so which is A divided by the volume of solids, that is thickness of plate, times the area. So area gets cancelled from the numerator and denominator. So essentially the void ratio is simply 2 times thickness of diffuse double layer divided by the thickness of the plate. If diffuse double layer thickness and thickness of the plate are known, we can estimate the void ratio. However, we can avoid estimation of thickness of plate and plate by considering specific surface area, which can be determined in the laboratory. So the specific surface area is nothing but surface area per unit mass, which has units of meter square per gram. So here, if I take the surface area of individual particle or platelet, surface area consists of this area, and area of the edges. If I ignore the area of edges, you have 2 times area divided by mass of solids. If I multiply with volume of solids and divide with volume of solids, I can write this as 2A divided by density of solids, and this volume of solids again I can write it as, this is density, and this volume of solids again I can write it as Tp times area. Again area gets cancelled, and so therefore specific surface area is nothing but 2 divided by density of solids times thickness of platelet. I can replace this thickness of platelet from the previous equation. Now I can write void ratio as D times rho S times SSA. So we got rid of Tp now, thickness of platelet now, or this can be written as D times specific gravity times rho W times surface area, specific surface area. Generally the specific surface area of clays like bentonates is very high, which can be as high as 800 meters square per gram. So therefore this is significantly higher value, maybe 800 meters square per gram. So this is the density of water, 1 gram per centimeter cube, and this is a constant value, it may be around 2.7. This is thickness of diffusible air, which can be several orders of magnitude higher than the thickness of the plate. This may be around 50 times if we assume, then 500 angstrom units or 1000 angstrom units we can use. And then if you calculate, the void ratios will be significantly high. They can be as high as more than 100. So similarly, this void ratio can be related to the equilibrium sediment volume, because this is the total volume, and knowing the total volume and volume of solids, we can relate this to void ratio. So therefore void ratio is related to the thickness of diffusible air and specific surface area, because once there is a formation of diffusible air around the clay platelet, so the interaction of these two diffusible layers would govern total volume of the soil. So as this diffusible air thickness is significantly high, the volume is significantly high. So this can be verified by conducting an experiment in kerosene, which is non-polar, so therefore there is no formation of diffusible layers. So when you conduct the experiment, the equilibrium volume is significantly lower. So this or equilibrium volume in water and equilibrium volume in kerosene or any other non-polar liquids. So the difference between these two volumes would infer or would tell you the swell potential of the soil, or how much it can significantly swell due to the clay water interaction or due to the formation of diffusible layers. So this is the difference between the equilibrium sediment volume of bentonite in water and kerosene. In case of water, the equilibrium sediment volume is significantly high, somewhere here. Still soil is about to settle and still it hasn't come to equilibrium, and it may take further some more days. But anyways, the equilibrium sediment volume will be somewhere here. So this is the volume around 55 ml, around 58 ml is the volume. When 2 gram of dry bentonite powder is mixed with water, the equilibrium sediment volume is nearly 58 ml. So when the same powder, same 2 gram of bentonite powder, when it is mixed with kerosene, so the volume is significantly low. So this is the volume of clay when there is no formation of diffused layers. So the volume is non-measurable by this one because this is much lower than even 5 mm. So this shows the swell potential of bentonite in the presence of water. We have been discussing the volume change behavior of kaolinite. Kaolinite, in a peculiar manner it behaves. It does not swell, however, it collapses or it exhibits collapse in the presence of water, or water which has a pH higher than isoelectric point of the edge. So generally if you take distilled water, the isoelectric point of the edges is about 3 to 4, and the distilled water pH is around 7, or sometimes it may vary between 6.5 and 7. So therefore, due to the changes in the charge and the particles, the particle interaction is different, therefore it exhibits a different behavior. So if I consider kaolinite particle or platelet, so the particle thickness or platelet thickness would be around 10 nanometer or nearly 100 angstrom units, which is nearly 10 times larger than the smectate particle, which is seen from the scanning electron microscope. So now particle thickness is larger, therefore the specific surface area is small. The specific surface area is smaller compared to the smectate, and the specific surface area varies in the range of 10 to 12 for kaolinite, and illite is in between. The specific surface area is about 18 meter square per gram. So because the thickness of the particle would govern the surface area or would influence the specific surface area. So the particles have smaller surface area, and the cation exchange capacity is also small because there is a strong bond between individual basic units of kaolinite, or the 1:1 mineral. So therefore the charge is also compensated, except that there is a small charge which is due to the isomorphous substitution, which is called permanent charge, but which is smaller value. So the CEC is, the cation exchange capacity is about 5 milliequivalent per 100 gram. Apart from the permanent charge, the charges on the kaolinite platelets would change depending on the interaction with different pore fluids. Edges generally have positive charge and face has negative charge. So therefore, when the particles interact in dry environment, particles would form or arrange themselves into this structure. This is called edge to face or card house structure. So this may be another cluster of particles, and these are another particle. So if you see, there is a macropore volume that exists between individual clay platelets, and there is a micropore volume and there is a macropore volume. So if kaolinite is mixed with kerosene in a cylinder, the platelets would arrange themselves in this manner. An edge to face interaction they have, and the particle or the equilibrium volume is higher because here the particles would not interact with the fluid, so therefore the volume is higher. However, if the distilled water is used in place of kerosene, so distilled water which has a pH higher than the isoelectric point of the edges, the charge of the edge would change to negative. So therefore now edges and particle face both have negative charge, therefore particles would arrange themselves into face to face manner. So therefore in the same jar, when water is mixed with when kaolinite is mixed with water, the particles would arrange themselves into face to face manner. So final sediment volume is smaller. This is the equilibrium sediment volume. Essentially, the kyelinate and bentonite, when they are mixed with water, the particle arrangement is face to face only. They are in dispersed condition. However, in case of kyelinate, because diffuse double layer does not exist around the clay platelet, because low surface area and low CEC, so the volume is smaller. In case of bentonite, due to high surface charge, the diffuse double layer thickness is larger, the high volume is very high. So therefore, when it is compared with kerosene, volume is much lower, and it appears that so therefore the volume is lower. Compacted state, when kyelinate is in a compacted state, when a structure is built on a kyelinate, it can take whatever the load that is put on the soil in dry state. But however, when the soil is saturated, the structure of the kyelinate would change to face arrangement, and which causes collapse of the soil. Here the kyelinate is mixed with water, and the kyelinate platelets now they would disperse and finally settle with time, and at equilibrium this is the volume that is exhibited by the kyelinate. So the volume is about 18 ml in water. So there is a clear solution that is formed, and but as the pH value increases, so there is a lot of dispersion that takes place, and the clear solution may not be visible. So in case of kerosene, the volume is higher. The volume is about 28 ml. Again, the volume of the equilibrium sediment volume would vary with amount of kyelinate mineral that is present in hyaline soil and the surface properties. So when the kyelinate is mixed with water, so there is a dispersion that forms because particles are now arranged in face to face manner. So it would take enormous time to settle and come to equilibrium. So when it comes to equilibrium, there is a thickness of sediment volume would be much higher compared to kerosene, or much higher compared to the sediment volume in the presence of kerosene. So the dispersion still after formation of this equilibrium volume, there is some dispersion usually that is left above the clear solution or beneath this clear solution. So this is the moisture sensor called EC5 developed by Decagon, which is an inexpensive sensor for measurement of moisture content in the field and laboratory. This determines the volumetric water content directly based on the dielectric property of the soil using capacitance principle. So you can also obtain the dielectric properties of different fluids. If you immerse it in water, based on the dielectric property it will give you the volumetric water content, and if you put it in kerosene, as the dielectric constant is much smaller or significantly lower compared to water, the volumetric water content also changes. So apart from this, this can be directly embedded in soil, in the field or in the laboratory columns to estimate the volumetric water content with changes in the moisture content. So this is another moisture sensor called Phytium, which is also developed by Decagon. So these two sensors can be used in the soil for the estimation of volumetric water content. So now we will demonstrate how the sensors respond in the presence of water, in the presence of soil with different moisture contents. The Phytium moisture sensor is connected to data logger called EM50. Now this is connected to a computer to read the data. The data logger can record and store the data for very long time. So currently it shows the value is nearly close to 0. So the volumetric water content is close to 0, which is volume of water by total volume. So it is meter cube per meter cube. Now the sensor will be dipped in water. Let us observe the change in the reading. When the sensor is dipped, the reading changes to close to 1. So which is validating whether the sensor is working or not. Now this sensor will be dipped in soil, and soil will be flooded, and the moisture content will be changed within the soil so that we can record the readings. Now here the sensor will be embedded in the column where sand is poured. Here the sand is poured at very loose density. Then the sensor will be embedded. Sensor will be directly kept in the soil. The orientation of the sensor could be in any direction. It could be horizontal or vertical, but however the orientation of the sensor should be perpendicular to the soil axis. Otherwise, when there is a movement of water, that would influence the readings of the sensor. So this way the sensor can be embedded. This is now the sensor is embedded in soil. The sensor is connected to the data logger. Now we are set to go. Now we connect this column with a water reservoir. When the water enters into the sand column, the changes in the moisture readings, let us observe. Now the column is connected to a water reservoir, so that can be seen here. When we allow the water to flow, so water slowly enters into the sand. We can see the movement of water into the soil column. So now water raises in the sand column. So the movement of water can be clearly seen. Now water raises slowly and reaches the sensor, and as the water comes near to the sensor, the readings of the volumetric water content would change. The sensors have very small radius of influence, so when the water enters into that zone, the volumetric water content will start changing. Now you can see the changes in the water content. The volumetric water content is about 0.163 now. This will be continuously stored. The data, volumetric water content data will be continuously stored. But if we want to see it, we need to scan it and then see at any given point what is the volumetric water content. So that value has changed now to 0.306. So that will keep changing, and at the end of the test we can plot the changes in the volumetric water content with time at the place where the sensor is embedded in the soil. We are not able to see a sharp wetting front here because soil is compacted in a loose state, and then the densities would slightly change, and therefore there are some fringes that appear here. So the volumetric water content is nearly 0.346, 0.516 now. A sharp variation in the color can be seen in the soil. This movement of water also can be predicted if the head is constant using green endamped method, provided the saturated water content of the sand is known and the initial head of the soil is known. Now theta value reaches to 0.356, slightly increased to 0.36 because the head reduced, the hydraulic gradient reduced, so the movement is slower now. Here we are not maintaining any constant head. So therefore this moisture sensor is very useful even in the field to determine the movement of water or the variation in the moisture content within the soil with time due to rainfall, infiltration or any other conditions, so that it can be used in wetting induced landslides problems. This is a T8 tensiometer. The tensiometer, generally the basic tensiometer has a higher entry porous disc. Now the tip can be shown. This tip is immersed in distilled water, and this higher entry disc would not allow the air to enter into the system until the matrix suction reaches the air entry pressure of the porous disc. So now this is the whole system, and which is connected to one water reservoir inside, and sensor to read the negative pressure which is transmitted through the porous disc when it is connected to a soil column or when it is connected to a soil which contains negative water pressure. So this is a whole setup. This is a T8 tensiometer, a digital one, which is developed by Decagon again, which can be connected to a data logger, and the readings can be read. The tensiometer, it can measure in the range of nearly 1 kilopascal to 100 kilopascal. However, the cavitation would limit its measurement range to go beyond 100 kilopascal. Even though the air entry of the higher entry disc allows it to use for more than 100 kilopascal, the cavitation pressure, which is nearly the atmospheric pressure minus the vapor pressure, this value is smaller than 100 kilopascal, which would limit the application of this tensiometer for measuring the suction value beyond 100 kilopascal. Due to dissolved salts, etc., the range of this particular tensiometer will again decrease. So this tensiometer can be readily used in the field along with moisture sensors for establishing soil water characteristic curve or to observe the changes in the suction with time. However, the response time of the tensiometer is different from response time of the moisture sensors. Moisture sensors respond quickly compared to tensiometers. So these tensiometers response time varies with the initial condition of the tensiometer and the moisture content in the soil. So the hydraulic equilibrium, when it has to establish the hydraulic equilibrium time would be equivalent to your response time. So hydraulic equilibrium time would be higher in case of expansive soils. So therefore it takes several minutes to hours to get an equilibrium value. On the other hand, the moisture sensors reads immediately, so therefore the caution should be followed to obtain equilibrium moisture content and equilibrium suction values in the laboratory, but from the field data when we read, the data may be not accurate, or the data would not allow you to relate the moisture content and suction immediately because response times are different. This is an MPS6 sensor which is developed by Decagon. So this is also to measure soil water potential or matrix suction in the field and laboratory. This can be embedded in soil just like the other moisture sensors, and if you look at the size compared to the tensiometer, the size is very small, and this is inexpensive, and this can be readily used in the field. The range of suctions it can measure would vary from 9 kilopascal lowest suction to maximum value of 100,000 kilopascal. So this is 100 MPa, 100 megapascals, which is given by company. So this has fixed matrix porous ceramic discs, 2 discs which are placed of these discs have size of 36 mm, and in between there is a printed circuit board, and outside you will have stainless steel screens. Now when this is embedded, there is a hydraulic equilibrium between the sensor and the soil that takes place. The sensors are first of all very useful for estimating the matrix suctions or soil water potentials in highly expansive clays, because the suction range vary significantly for these soils. However, recent studies by Tripathi et al. In 2016 showed that the sensors would not respond correctly beyond 3000 kilopascal or 3 MPa when it is compared, the values are compared with WP4 or hygrometer readings, because initially when the sensor is wet, the moisture flows from the sensor to the soil. So during that time the surrounding soil swells and the moisture flow stops. So because of that the readings are not accurate. So on the other hand, when the sensor is initially dry but the soil is wet, when the moisture movement takes place from the soil to the sensor, soil volume decreases, due to which there is a discontinuity with the soil, due to which there are some measurement errors. So even though this is a inexpensive sensor that could be used for measuring the matrix suction in the field, it has several limitations due to workability conditions in the field. Now we have kept moisture sensor and tensiometer in the column, and we are filling sandy soil. Sand is filled to nearly top level. Now this is leveled and now it's ready. Now we'll allow the water to flow through by connecting it to a reservoir. So now this is connected to a reservoir. Now water is going into the column due to the provided hydraulic gradient. Now let us see how the readings change. So the first port is connected to the tensiometer and second port is connected to 5TM. That can be seen here. So the first port has a value of suction equal to minus 19 kilopascal, and the volumetric water current is 0.057 meter cube per meter cube. Scan. Now as more water infiltrates, the readings change. Now the new reading is 0.211 for the moisture sensor and suction is nearly same, 20.89. So the response time of the tensiometer is higher, so therefore the suction value is not changing even though the water level is changing. So the moisture content value is changing, so therefore we cannot directly use moisture content and suction data to establish SWCC from this method. The moisture content now changed to 0.315 and where the tensiometer reading is 21.57 kilopascal. So it can be seen that the response times for these two sensors are different. This is a vapor equilibrium technique where the soil sample is kept in a closed desiccator, and at the bottom a salt solution is placed, and we can clearly see the soil sample which is kept above the salt solution. However, the vapors of the salt solution interact with the soil, and depending on the vapor pressure of the salt solution, either moisture will be taken from the soil or moisture will be absorbed by the soil. Finally, after equilibrium, the vapor pressure of the soil pore water will be same as the vapor pressure of the salt solution. We can place different salt solution at the bottom, salt solutions at the bottom with different concentrations. So therefore they exert different vapor pressures on the salt sample. So the vapor pressures of the salt solutions can be determined using WP4, where the solution can be kept in WP4 and directly the total suction value can be determined. Based on the relative humidity measurement from the WP4, the total suction will be obtained, and when this suction or the vapor pressure is in equilibrium with the soil pore water, soil also will have the same suction at equilibrium. So using different pore fluids at different equilibrium time intervals, whatever the water content soil achieves at the equilibrium time, one can establish the soil water characteristic curve on the drier side. So this is a useful technique, however it is highly time taking, but this could be the only alternative in laboratory for estimating the soil water characteristic curve on the dry sides. This technique is very useful to estimate to control the suctions to a high values as high as 300 megapascals. The technique is simple, but regularly we need to monitor the weight of the soil sample. Once the weight of the soil sample is constant, that means there is an equilibrium that is established between the salt solution and the sample. So then the soil sample moisture content can be obtained by putting it in oven, and the salt solution vapor pressure can be obtained from the WP4 technique, which gives the suction value within the soil sample, and suction and moisture content. When these two values are known, we obtain one data point on the SWCC on the drier side. So this is dew point potentiometer or WP4 designed by Degagan. This works based on the principle of measuring dew point due to condensation. Initially the soil may have particular vapor pressure. When the sample is kept inside this WP4 instrument or equipment, there is a closed chamber where you have a temperature controller. When the temperature is reduced drastically, it reaches the vapor pressure becomes equal to the saturated vapor pressure at one particular point under that particular temperature, which makes the formation of dew point. So that will be detected. So as soon as it is detected, it records the dew point temperature as well as initial temperature. Based on these two readings, it is possible to estimate the initial relative humidity of the soil pore system. So from that, using Kelvin's equation, it is possible to determine the total suction of the soil. So this can be calibrated using different salt solutions. When a KCl solution is used with a concentration of 0.5 at temperature 20, it gives a total suction value of 2.184, and same KCl when it is used at saturated solution, that is 342 grams of solute should be added in 1 liter of water, then it gives a suction value of 21.9. When the salt solution is taken and in a cup half full, when it is placed in this door and when you close it, the solution, and when you put it on, now the temperatures will be gradually reduced inside. Then this vapor pressure, wherever this is equal to the saturated vapor pressure, corresponding temperature is the dew point temperature. So that reading it gives. Here KCl 1 molar solution is used. So the corresponding suction value is 4.6 megapascal. Here we can see the changes in the temperature. So this is the relationship between vapor pressure and temperature in Kelvin. So this is the saturated vapor pressure curve. So when the sample is kept in WP4, initially the point A represents the sample condition. Sample has particular temperature and corresponding vapor pressure. As the sample is kept inside the WP4 chamber, the temperature is slowly dropped and it follows this line. When the temperature is decreased, it hits saturated vapor pressure curve at one particular temperature, which is called dew point. At that particular temperature, dew forms or condensation takes place. So that will be detected by this instrument. So when the dew point temperature is known and the initial temperature is known, from the available formula for saturated vapor pressure, knowing the temperature, one can estimate the saturated vapor pressure. This vapor pressure is actually attributed to the initial vapor pressure of the sample, and the corresponding saturated vapor pressure for the initial temperature will be obtained. From knowing the vapor pressure at the initial point and corresponding saturated pressure under the same temperature, one can estimate the relative humidity, and from that the total suction will be obtained, and that is what is reported by this instrument. So this is the relationship between relative humidity and total suction from Kelvin's equation. So here the sensitivity of the Kelvin's equation is given, and for different temperatures, the solid line is for temperature 20 degrees Celsius and the broken line is for 6 degrees Celsius. So as you can see, at relative humidity values of close to 95 or so, this is highly insensitive. For the variation of total suction from nearly 10 kilopascal to around more than 1000 kilopascal, the variation in relative humidity is negligible. So therefore, when the relative humidity is close to 100% or nearly above 95 or so, the values obtained from this particular technique is erroneous or not accurate. So on the higher side of the suction, this method is very useful because the sensitivity is very good, and the variation in the total suction with relative humidity are very sensitive. Therefore this particular technique can be used for the range perhaps more than 2000-3000 kilopascal to even up to 100 MPa, 100,000 kilopascal. So now the difference between sample temperature and the box temperature is nearly close to zero. Now after reaching minus 0.07, the difference between TS and TB. So now once you load it, it will display the measurement of suction. After some time it displays the reading. The total suction value is 2.1 megapascal. Now it started displaying the reading and it will change. The current temperature of the sample is 34.3 degrees Celsius. At equilibrium, it will show 4.6 megapascal for 1 molar KCl solution. Still it is showing the temperature variation in the sample temperature and the box temperature. When the temperature difference becomes negligible or close to zero, then dew formation takes place and it indicates the total suction value, or it gives the total suction value. Similarly, the soil sample will be loaded, which is filled in the same cup, half full, and again it has to come to equilibrium with the chamber, and once the temperature comes to equilibrium, once the condensation occurs, dew point forms and the corresponding vapor pressure will be recorded, and based on that the relative humidity will be estimated. Using the Kelvin's equation, the total suction will be displayed here. Similarly, for different soils at different moisture contents, total suction values can be obtained using this particular technique. Here the total suction can be obtained. In the earlier technique, using vapor equilibrium technique, we were controlling the total suction. Here total suction can be estimated for a known moisture content.